This will be a tutorial on network flow and the FORD-FULKERSON algorithm. A network is like a graph, but with flow flowing from a source vertex to a sink vertex, where the source vertex has no incoming edges and the sink has no outgoing edges. The capacity rule states that flow may not exceed edge capacity, and edge capacity is the edge weight. Conservation rule states that for every vertex except the source and the sink, the amount of flow going into a vertex is the same as the amount that's coming out. And that's only because the source has no incoming and the sink has no outgoing. So this just means that the flow is flowing into and it comes out of, and nothing's lost. Maximum flow is the most flow we can push through the network from S to T, where T is the sink and S is the source, given our capacity strengths. So maximum flow is the most we can push through given the capacities on our edges, those edge weights. So we must choose our paths wisely to maximize flow. This is a simple network, and these are edge capacities. So these are vertices. These are edges, they're directed edges, and these are capacities of those edges. Can you guess which vertices are source and sink based on those descriptions earlier? Well, this would be the sink, because the flow is originating here. There's no incoming edges into the sink. Sorry, the source. It originates at the source, and there's no incoming edges into the source. And the sink is where it all leads. No outgoing edges from the sink. It catches all the flow. So a cut is a partition of the network where the source is on one side of the partition and the sink is on the other side. So if we look back at our network, this is a cut. This is one partition. This is the other partition here. On one side of the partition is the source. On the other side is the sink. So a line that follows this mouse cursor through 2, 2, and 2, like so, that's not a cut because it's not partitioning the source separately from the sink. It has to separate the source from the sink, right? So an edge across the partition from source to sink is a forward edge. The reverse is a backward edge. So this starts on the sink side, this starts on the source side, goes across to the sink side. That's a forward edge based on the direction. Now suppose it was reversed, it went this way from right to left. That would be a reverse edge across the cut, but it's not, it's a forward edge. The capacity of a cut is the capacity of the forward edges across the cut. So that's 3, 1, and 2. So the capacity is 6. And the flow across the cut is the flow of forward edges minus the flow of backward edges. So these are just capacities right now, but eventually in a few slides it'll be filled with, say, 2/3, 2 out of 3. Maybe there's 2 flowing through this, or 1 out of 1, or 2 out of 2. And so the flow is counted. We sum the positive or the forward edges are being summed, the flow across that, and we're subtracting from that sum the backward edges. Like we said, suppose this was backward, we would subtract that. But if you're talking about just the capacity of the cut, don't worry about backward edges. So the residual capacity of a forward edge is the total capacity minus the current flow. For a backward edge, residual capacity is just current flow. So let's have a look here at the same network. We've sort of removed that cut. And now we've added in some flow. So residual capacity. Okay, let's talk about residual capacity. So this edge has a capacity of 7, but it's only accepting a flow of 2. So the residual capacity is 5. So we'll move on to an augmenting path, which is a path from source to sink with non-zero residual capacity. So if you can find a path from source to sink where over the entire path there's non-zero residual capacity, and what that means is the least residual capacity edge is the only one you count. So out of the whole path, this is 2 out of 7, 2 out of 2, 2 out of 2. Well, the least residual capacity is 0 in this one and this one. So this path actually has residual capacity, actually has residual capacity of 0 over the whole path. So it's not an augmenting path, because the path doesn't have non-zero residual capacity, has 0 residual capacity. This is not an augmenting path. This single edge does, but over this entire path, you take the single edge with the least residual capacity and you use that to tell if it's an augmenting path. If there exists an augmenting path, then there is a greater flow possible. If there is no augmenting path, then we have a maximum flow. The maximum flow of a network is equal to the capacity of the minimum cut. So pretty intuitive. If there's no augmenting path, then there's nowhere to push more flow through. So you have a maximum flow. And similarly, the maximum flow is equal to the capacity of the minimum cut. And remember here, this cut was actually a minimum because it was 3, 2, and 1. That's 6. Any other one, 5, 2, and 2, it's greater than 3, 1, and 7. Any way you want to cut this, or this is on one side, this is on the other side, this is the least. The edges have the least capacity. So 3, 1, and 2, yep. So the minimum cut is the maximum flow, because so the flow originates at the source, has to get to the sink. It has to pass through this cut, has to pass through all 3 of these edges. And so these 3 edges can only accept 6 in total. If there's 7 or 8 or 9, anything greater than 6, it's not going to get to the sink. Only 6 is going to get to the sink. No matter what, if you have 1,000,000 vertices and 10 million edges before, whatever you do doesn't matter. The minimum cut is equal to the maximum possible flow, because nothing more than the minimum cut is going to get through to that sink. So let's move on to the FORD-FULKERSON algorithm for maximum flow. FORD-FULKERSON accepts a network, and then we say for each edge in the network, the flow in that edge equals 0. Then we have a sort of do-while loop here. So what stop is false, and then we'll repeat this block here until stop is true. So the first thing we're going to do is traverse G using like a depth first search, starting at the source to find an augmenting path. If an augmenting path exists, we're going to compute its residual capacity. So this constant D is positive infinity. It's just a constant we're using. For each edge in the path, where Pi and P here are the same thing, it's the path. For each edge in the path, if the residual capacity of the edge is less than D, less than positive infinity, then we're going to assign D now, instead of positive infinity, it's going to be newly assigned to the residual capacity of E. So we're getting the residual capacity of those. And then for each edge in the path, if E is a forward edge, then the flow across that edge is going to be the flow that it already has plus the residual capacity, the amount that's left to pump through it. Else, if it's a backward edge, then the flow we're going to pump through it is going to be the flow minus D. Else, if there's no augmenting paths left, we're going to say stop is true and stop the algorithm. So the running time, the flow starts at 0. We set the flow to start at 0. Each time we find an augmenting path, we increase the flow by at least 1 because we're using integers. So the maximum flow is an upper bound. To find these augmented paths, we use a graph traversal like depth first search, which runs an OM time, where M is the number of edges in the graph. Therefore, the total running time is OF times M. So in the worst case, we're adding one unit of flow with per each depth first search. So per each augmented path, we're adding 1 unit of flow, and we can have as many as maximum flow units of flow. So that's the running time of that algorithm.